Good afternoon. Welcome back to the Thermodynamics lecture number 2. Today we'll see some more applications. Yesterday we have seen the system, surroundings, open system, closed system, isolated system, adiabatic process, isothermal process, first law of thermodynamics, state functions or variables, all those things. Now in the mathematical equation of the first law of thermodynamics, if you say work, most of the work we see as a pressure volume work, because most of the time we are dealing with the gases and more applications also in gases only. So our equation is delta U or delta E. Sometimes people are using this thing. So is equal to Q plus W. W will vary, depends upon the whether work is done on the system or work done by the system. That will be, sign will be different. Now, say for the small experiments we will consider, for that we will assume some 2-3 things. One is my reaction is, a chemical reaction is reversible. Reversible means I can change the all parameters reverse also. I can make it a reverse also. Infinitesimally small changes will be there. Those changes will be reversed at any point of time. So that reversible I am considering. Second thing I am considering is it is a pressure volume work. I am considering only pressure volume work. That is mechanical work I am telling. I am using a cylinder and a piston, and piston is a frictionless. No friction. Frictionless piston means it is not taking any energy. I am considering, I am assuming this. The fourth is ideal gas. Now take a cylinder, connect it with a piston, and piston is free, means it is frictionless. Have a gas of ideal gas whose volume is, initial volume is V. Sometimes people say Vi or Vf, V1. So I am also taking as a Vi, and external pressure is, you can take as a compression or expansion. So here I am taking as a compression. So initial volume is V1 or Vi. Final volume after compression is V2 or Vf. Then the piston travel is L, and piston area is A. These are the assumptions for this work. Now, work done on an ideal gas in a cylinder when it is compressed by a constant external pressure. External pressure is constant, but it is forcing on the piston. Right. Now, we know that volume equal to L into A, and force per unit area equal to pressure, P equal to force per unit area. From this, what I can write is, wherever the applicable, I can write pressure equal to pressure equal to force per unit area. Now, considering this, work done for reversible, and it is a integral V initial to V final P dV. P is P external. Here I am considering as a compression. So why integral I am taking? Every minute it is coming down. What is coming down? The difference of the pressure is coming down, and the volume of the system is coming down. But pressure is going to equalize till it is equal external pressure and internal pressure. So the sum, for the summation, normally in the mathematics we write it as an integral. So W reverse work equal to P delta P. Now this same thing, the expansion also we can write P internal pressure of the gas dV, and like the same thing. If you write P as a, we know P equal to nRT by V. So same thing I am replacing Vi by Vf. P external I am replacing with nRT by V into dV. Nothing but nRT I am taking out, integral Vi dV by V. V final equal to 2.303 RT log, this is log 10 base, V2 by or Vf by V initial, that is work reversible. So this is the equation what normally we are using for in the mechanical work for a reversible. If it is not reversible, if it is irreversible, then it is simply work equal to P delta V. If it is a normal one, if it is a reversible one, it is 2.303 RT log based on Vf by Vi. Now, here some more information we are giving. If a gas is expanding freely, then work done equal to 0, and energy Q equal to heat equal to 0. Delta U, that is internal energy, also 0. It is a free expansion. Okay. Now, for adiabatic change, Q equal to 0, that means there is no change of the heat inside the outside. So in that case, delta U equal to work adiabatic. These are the old one only, but additionally we are seeing this one. Okay. Now we are going to introduce one more state function, that is enthalpy or H. Enthalpy. This one is so far we are seeing the internal energy and heat and work. Thermodynamics, most of the time thermochemistry is based on this only. Enthalpy or H, one more parameter. Why this parameter is required? This parameter is required so far we are dealing with the constant volume. Most of the reactions in the gases equations, so volume will not be constant, pressure will be constant in the chemical reactions. So we will see how this can be defined or this will be useful. Now again go back to the formula for delta U or delta E equal to Q minus W. W is a work and all. Work done and work done, sometimes we are writing Q plus also, don't get confused. Now delta U is nothing but U2 or U2 minus U1 change, and at constant pressure QP means I am giving the heat at constant pressure, so there will be a change in work, that is P delta V, replacing this equation as QP into minus P delta V or dV, nothing but V2 minus V1. This again I am writing P minus P V2 minus V1. Sometimes I am writing I and F, sometimes I am writing 2 and 1, both are same, final and initial or the second one and first one. Now if I am writing the QP, bringing it this side, U2 plus PV2 minus of U1 plus PV1, nothing but if I am defining as UPV, H equal to U plus PV, if I am defining, that is H as enthalpy, it is the H2 minus H1. This is one more parameter we are introducing. Meaning of this is, see, in a chemical reaction, when you are giving a heat, there will be some work and there will be some internal energy. That means internal energy and work together is called the enthalpy. If it is only internal energy, that will be the normal volume constant, means here it is constant, so only internal energy will be there. Here it is internal energy, there will be a change in internal energy and there is a change in volume also. So that will be the normal in chemical equations, enthalpy, which is a state function, which is a this thing. And last this thing is delta H is negative for exothermic. Delta H is, this is delta H QP is nothing but delta H I am taking. Delta H H2 minus H1. Delta H is positive, is endothermic. That means if the product's heat content is less than the reactant's constant, that is exothermic. If the product content heat content is more than the reactants, it is endothermic. Heat is taken. So we will see some more tomorrow, heat capacities and all. Thank you very much.